Before we talk about these formulas, I want us to kind of get an idea about what angular speed is. And I think that one of the better examples that you're going to see for this is with a carousel. We're going to do a problem with a carousel later, you know, the big merry-go-round with the horses that go up and down and around and around. If you have, and you don't need to write this down, you've got this carousel and you've got a horse here and a horse here and a horse here, and it's your Ferris or your merry-go-round is going around, and you're going to be, let's look at this as it's going 1/4 of a turn. So this horse ends up being here. This horse ends up being here, and this horse ends up being over here. It's kind of obvious that this distance this horse travels is longer than this distance, right? Did they take the same time to get from here to here? Yes. So if we're looking at this just with a linear speed, then we know that we'd say this horse is going faster than this horse because it's traveling a farther distance in the same amount of time. So its speed has to be faster. But if we're looking at this in terms of angles, if it's going from straight up to straight west, then it's going 90 degrees. Each of these horses are doing 1/4 of a revolution in that amount of time. So we could say that they're all going the same speed when we're looking at the change of the angle, because their angles are all going to be a 90-degree change. So there's a couple of different ways to look at speeds there. How the distance that they've traveled or the angle measure that they've traveled. And that's where we get linear speed as opposed to angular speed. So anybody that's been in marching band knows that, you know, when you're in a parade and you have to turn a corner, this person here that's in the center is basically just marching in place and just turning, and this person over here is really having to do most of the work and most of the steps in order to get around that corner. Okay, so that is where we're going to be talking about these formulas. If a point is in motion on a circle of radius r through the angle of theta radians in time t, s is the arc length, its linear speed is v for velocity over s divided by t. Its angular speed is omega equals theta divided by t. So this is the omega symbol. Y'all are probably familiar with the omega symbol that looks like this. You know, a lot of fraternities and sororities have that omega symbol. That's like the uppercase, and this is the lowercase. Linear speed, right, just like you learned from elementary school, is how fast you're going with distance related to time, like feet per second or miles per hour. And angular speed measures how fast the angle measure changes with respect to time, like radians per second, degrees per minute, like that. Okay, so we can relate these two speeds by using this arc length formula. And our basic definition of speed, like I said, that we've learned from elementary school, speed is distance divided by time. So my distance is an arc length. So let's look at this distance as S equals R theta. And we're going to figure out where these formulas come from and hopefully understand how they relate. That's my distance. If I take the distance and divide it by time, I will get my speed. So I'm taking this distance here, dividing it by time, and do that on both sides of that equation. Distance divided by time, distance divided by time is my speed. This is an arc length that we would measure like we would normally measure us walking across the floor, with either in feet or inches or meters or miles. This is a regular speed here then. So this is my velocity. I'm going to rewrite this to where the R is first. And then I have theta divided by t. So that theta is my angle measure. And that angle measure is going to be divided by time. That's what I'm calling my angular speed. So basically how these relate, I'm going to just rewrite this formula over here just because I kind of ran out of room. Linear speed is equal to the radius times angular speed. Okay. Linear speed is the radius times the angular speed. And we're basically going to be using this formula here in order to do a few word problems. Now, this first problem is just asking me to change units of measurement, express the following angular speed in radians per second. So I'm just converting the units of measurement on this problem, right? Okay, this is talking about 1 revolution per second. Well, we haven't really talked a whole lot about the word revolution here. 1 revolution is 360 degrees or 2 pi radians. They're all equal. All 3 of those are representing all the way around, right? All of these are equal. Well, I want to convert 7 revolutions to 7 revolutions per second to radians per second. Before, we have been changing degrees to radians and radians to degrees. So here we're just using a different measurement of revolution. So we're going to start off this problem kind of like we did our other problems. Write down what we're given. And I'm going to multiply that fraction times an equivalent fraction that's equal to 1. Now, I want revolutions to cancel out and go away. So I need revolutions here on the bottom. And I want to end up in radians per second. So I need radians in the top part of the fraction. I've already got the seconds in the bottom part of the fraction. So looking over here, I know that 2 pi radians is 1 revolution. So I can see the revolutions are going to cancel, and this is going to be 14 pi radians per second. Now, this is the long way to do it with dimensional analysis. You could also set this up as a proportion and solve it that way and get 14 pi. It doesn't really matter to me how you do it. So this is just converting revolutions to radians.
Problem 4, the blades of a fan rotate at 500 revolutions per minute and have a diameter of 8 inches. Find the linear speed in inches per minute of a point on the tip of the fan blade and use 3.1416 as the value for pi. So one of the first things I want you to notice is that you are given revolutions per minute, and you need to know that that is an angular speed. Also notice that you're given the diameter, not the radius. So to find the radius, we just take this number, divide it by 2. So my radius is going to be 4. I am asked to find the linear speed. So this is my formula I'm going to be using. I know that my radius is 4, and I need my angular speed in radians. Right now, it's in terms of revolutions per minute. So I'm going to take this 500 revolutions per 1 minute and change that to radians per minute. So when I multiply by 2 pi radians over 1 revolution, revolutions are going to cancel. So I can multiply straight across. 500 times 2 pi is 1,000 pi, and that's going to be radians per minute. So my angular speed is 1,000 pi. So when I multiply 4 times 1,000 pi, I get 4,000 pi, and that is going to be approximately 12,566.4 inches per minute. Problem 5, the angular speed of a point on Earth is pi divided by 12 radians per hour. The equator lies on a circle of radius 4,000 miles. And in this first part of the problem, I want to find the linear velocity of a point that is on the equator. So I can look at, say, this point right here, and the distance between this point and the center of the Earth is 4,000 miles. And as the Earth rotates, this point is going to rotate somewhere over here, and I'm asked to find this angle measure within that angle. So again, I'm asked to find the linear velocity. This is my formula that I'm using. And I know the radius is 4,000. And my angular speed has to be in units of radians per hour, radians per minute, radians per some unit of time. And I have radians per hour here, so pi over 12. When I multiply this out, I get approximately 1,047 miles per hour. And the second part of this problem is asking me, in the relation at that particular point on the equator, what happens every 24 hours? Well, I'm moving at a rate of pi 12 radians per hour as far as the angular measures go. So in 24 hours, I will go to pi. So that distance that this point travels is all the way around that circle. So the point travels 2 pi radians, which is equivalent to 1 full rotation, or 1 day. Problem 6. Find the angular velocity in radians per minute and linear velocity in inches per minute for a point on the edge of a record spinning at 46 revolutions per minute. Okay. So there's two things that I'm asked to find. Now, the information that I'm given is how fast this is spinning in revolutions per minute. So I am given an angular velocity. I just need to change this revolutions per minute into radians per minute. So my angular velocity is 46 revolutions in 1 minute, and I am changing that by multiplying by something where the revolutions will cancel, and I end up with radians. So I'm going to be multiplying by 2 pi over 1, right? Because 2 pi radians is 1 revolution. And then I can see that revolutions are going to cancel. So I end up with 46 times 2 pi, which is 92 pi radians per minute, and that's my exact value. And if I wanted to round that, that is going to be approximately 289 radians per minute. So now that I have my angular velocity in terms of radians per some unit of time, now I can find my linear velocity. Linear velocity is the radius times the angular velocity. And the radius here is half of 6.1. So I'm going to take 6.1, divide that by 2, and then multiply that by 289. And I get approximately 881.5, and this is going to be inches per minute.
Okay, next problem. A water wheel has a radius of 12 feet. The wheel is rotating at 20 revolutions per minute. Find the linear speed in feet per minute of the water and round to the nearest whole number. Okay, so I have 20 revolutions in 1 minute times 2 pi radians over 1 revolution. We're just changing units of measurement. We're just converting units of measurements from changing from revolutions to radians. So this is 40 pi radians per minute. This is my angular speed. Because it's talking about the change in the angle measure with respect to time. Let me zoom in there. You can see that a little bit better. Now I put that information into my formula along with this information up here where I have the radius is 12 feet. Okay. Linear is the radius times my angular speed. So it's going to be 12 times 40 pi. And I'm not sure on this problem, but I think that we're just getting our answer to the nearest whole number here in my math lab. If you needed to get the answer in terms of pi, that's easy. It's 480 times pi. So I'm going to do 480 times pi, and that's going to give me 1508 feet per minute. Any questions with that? Okay, the next problem. On a carousel, the outer row of animals is 24 feet from the center. And the inner row is 15 feet from the center. Carousel is rotating at 2.7 revolutions per minute. So it's going around almost 3 times a minute. What is the difference in feet per mile in the linear speeds of the animals? I'm supposed to say in the outer and inner rows and round to the nearest foot per minute. So I've got my outer row of animals here. And this radius is 24. And then I've got my inner row of animals here. And this radius is 15. So I need to figure out the speed of the animal here on the outer row and the speed of the animal here on the inner row and subtract them to figure out their difference. So the first thing I need to do is to change from revolutions to radians, revolutions per minute to radians per minute. So I have 2.7 revolutions in 1 minute times 2 pi radians over 1 revolution. We're just changing units of measure, just like you're changing feet to inches or meters to kilometers, hours to minutes, right? We're just changing our units of measurement. Revolutions cancel. 2.7 times 2 is 5.4. So I have 5.4 pi radians per minute. That is my angular speed. This is my angular speed. The question is asking me the difference in the linear speeds of those two animals. So I have to find the linear speed of the outside animal or outer animal. And I also have to find the linear speed of the inner animal. And then once I find those two, then I can subtract them. So again, here's my formula. Velocity is radius times omega. So the velocity of this outer animal is going to be 24 times 5.4 pi. Double check that. 24 times 5.4, yep, 129.6 pi. And then for the inner animal, my speed is going to be 15 times 5.4 pi. And that is 81 times pi. So now I know their speeds. I can subtract them to find the difference. So I'm going to do 129.6 pi minus 81 pi. And that's going to give me 48.6 pi. That's the difference in their speeds. And if I want to get this to the nearest foot per minute, that's going to be 153 feet per minute.